Okay, in this chapter, in this section, we're going to stretch your capacity for visualization. We're going to talk about Lagrange's theorem, which takes this idea of layers one step further. So at the beginning of the chapter, we compared cosets to layers of an onion. But an even better analogy is to slices of a loaf of sandwich bread. Because as we'll see in this section, every coset of a particular subgroup within a given group has exactly the same size. So you should be thinking about, here's your group. Right? This is my loaf of sandwich bread, and my cosets are partitioning this group into slices of exactly the same size. Now, if you're talking about a discrete group, you can think of raisins within the loaf of bread. Maybe this one has 4 raisins, and this one also has 4 raisins. This one also has 4 raisins. So the number of raisins in each slice is the same. Now, of course, in a real loaf of raisin bread, that's a miracle, but it works out in groups that each coset will have exactly the same number of elements. Okay. So we'll be talking about left cosets, but everything we say will be true also of right cosets. Now, to show two sets have the same size, our typical tool is to construct a bijection between the two sets. And if there's a bijection, they'll have the same number of elements. Of course, that's true if the two sets are finite. If you have a set that has 5 elements, you have a bijection to another set that has 5 elements, then that other set will have 5 elements. Now, for infinite sets, we would also say they have the same size in some sense, even though infinity is not really a definite number like 5 or 7 is. So in this proposition, we're constructing a map from a subgroup to a coset, and we'll show that this map is a bijection. Basically, if a map is invertible, it's a bijection. So we can find the inverse of the map and show that the map is a bijection. In this proof, we show the map is 1-to-1 and onto. All right. So following this theorem, we get that the coset and the subgroup have the same number of elements. So Lagrange's theorem simply says that these cosets evenly divide the group into a certain number of classes. That since there's the same number of, well, let's go back to the picture here. If I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I have 9 slices and there are 4 raisins in each slice, how many raisins do I have? Well, I have 36 because that's 9 times, what did I say? 9 times 4. Yeah, so 36 is 9 times 4. So 36 is equal to 9 times 4. And what that means is that 36 is the order of the group, 4 is the order of the subgroup, and 9 is the number of cosets, which is G 2 dots H. Sorry for the messy writing, but you can see the relationship between the number of elements in the big group and the number of elements in the subgroup. The ratio between those two numbers is the index, or number of cosets. Each coset is a copy of the subgroup, so it divides the group up evenly. Right? So that's the whole essence of this theorem here, that the order of G divided by the order of H is equal to the number of cosets. All right, and you'd be surprised how far this takes you. It really gives you a lot of information about groups. A very far-reaching theorem. Right. So if we do an example, let G be a group with order of G equals 25, then since 2 doesn't divide 25 evenly, Lagrange's theorem implies G can't possibly have a subgroup with 2 elements. Now, isn't that amazing? I can tell something about the non-existence of groups just by looking at the number of elements in the group. Okay, I know there's no subgroup of order 2. No, there's no subgroup of order 3. There's no subgroup of order 9. There's no subgroup of order 11. All those that's true because none of those numbers divide 25. In fact, the only subgroup I can have is order 5. So that really cuts down my options. Okay. All right, now you can actually go one step further. If you have a group G, let's draw a picture here, and inside of G you have H, and inside of H you have K, and K has cosets in H, and H has cosets in G. Well, the number of copies of K in H will be H colon K. So there's H colon K sub cosets of K in H. However, H itself has cosets. Each one of those cosets of H will have H colon K cosets of K. So the number of cosets of K in G is equal to the number of cosets of K in H times the number of cosets of H in G. All right, so that's kind of a picture that H is divided up into cosets of G. And each one of these copies of H, let me call this GH, each one of these copies of H is divided up in the same way into cosets of H, of K, right? So the same number of cosets of K in this set as in this set. So the cosets of K divide up evenly each coset of H. So that's how we get this relation. Right, so we'll be doing more with this later on, but this is our introduction to Lagrange's theorem.